Hi folks, we're looking at radicals, which are actually in the MathSL curriculum, exponents and radicals, but we're taking a look at them a little further than the curriculum requires. In some cases though, we are going to gloss over a few of the rules because you can kind of get lost in this stuff very easily. Alright, so I call this nitpicking radicals, looking for the little rules. Simplify the square root of 3 squared. You'd probably say, well, that's the square root of 9, which is 3. If I ask you to square root negative 3 all squared, then you'd say that's the square root of 9, which is 3. But that's kind of weird because we expect square rooting and squaring to be opposite operations, so that they should, if you like the term, cancel each other out. They only work seamlessly that way if we're dealing with radicals of positive numbers. Okay? If we took one more look at this and say we wanted to do this, the square root of negative 3 all squared, you'd probably say that's not possible. I can't do it in that order. So if we wanted to refine our conception of the square root of a squared, we could say the square root of a squared is actually the absolute value of a, but it's not necessarily equal to a. And then that will be true when you're dealing with a lot of the even roots. It won't be an issue if you're dealing with odd roots. So if I have the cube root of negative 3 all cubed, that's the same as cube root of negative 27, which works out to negative 3. That's fine. No issues. Okay. Or instead of dealing with these situations on a case-by-case basis, we can say most of the time we're going to dig into radicals only in the context of positive numbers. Now, it seems like a bit of a cop-out, but for now, that's what we'll do. So, only dig into radicals with positive values. In order to simplify radicals, we need to use what I'd say is common sense, but it's also pretty abstract at the same time. So we're going to simplify assuming that x is greater than 0 and y is greater than 0. So assuming that no problems are going to crop up with positivity and negativity and needing absolute value signs. What I want you to do when you have a problem like this is split it into two parts. Parts that have perfect square roots and parts that don't. So out of 98, you could take out 49. That has a perfect square root. And you'd have leftovers of 2. Out of the x cubed term, x squared has a square root, and that has leftovers of an x. Out of y to the 5th, y squared has a square root, but so does y to the 4th. So leftovers of y in that case. And since we can split things apart with radicals, one of our rules was root ab is the same as root a times root b. Again, assuming we've got positive values. Now we can simplify what's on the left. Square root of 49 is 7. X, y squared by the square root of 2xy. Now, you might say, why would I ever do that? Really, it's just an issue of aesthetics, of liking the way it looks that way. All right. The next one is the cube root. So you might have to know your perfect cubes. 32 is fishy, so what kind of cubes might we be looking for? Maybe 2 cubed, which is 8. Okay. The x to the 8th. Yeah, you could take an x cubed, but you could take another x cubed as well. So x to the 6th is going to be useful. And y to the 9th has a cube root. That's good. What are our leftovers? We took out 8 from 32, so we took out a factor of 8. Leaves us with a factor of 4. We took out a factor of x to the 6th, so we're left with an x squared. And we took out all of the y's. So the cube root of 8 is 2. Cube root of x to the 6th is x squared. And we have y cubed. And we get times the cube root of 4x squared. We might also have rational expressions involving roots. So in this case, we actually already did the bottom of this one. So We're going to simplify the bottom first. Turned out to be 7xy squared times the root of 2xy. So just like this, we ended up with that on the bottom. We don't like square roots on the bottom because it's a weird thing to think of dividing by. We want to be dividing by, ideally, positive integers. And, if necessary, some variables. So to get rid of that square root sign, I'm going to have to multiply by root 2xy. And if I do it on the top, or on the bottom, I'll have to do it on the top as well. Here's what we end up with. The square root of 6 x squared y all over 7xy squared. And if you have root 2xy times root 2xy, you just end up with 2xy. Okay, let's see if we can simplify the top here. So that's equal to the square root of x squared times root 6y. The bottom would have been 14x squared y cubed. Let's take it down here. That means we've got x root 6y all over 14x squared y cubed, and divide out your x's. Okay. Pretty straightforward when we're dealing with square roots. To get rid of a square root, all you have to do is multiply by the exact same thing. So root 2xy times root 2xy just made 2xy. All right, in the next one, we're going to end up with another expression that we've already factored on the bottom. So I showed in question B that this bottom, or this denominator, becomes 2x squared y cubed times the cube root of 4x squared. Okay. Now what we need to do is get rid of that cube root. So I need to make perfect cubes on the bottom. I've got a 4. In order to make a perfect cube, I could times that by 2. I'll get an 8. That's a perfect cube. I've got an x squared. I want to make an x cubed, so I'll have to multiply by x in order to make an x cubed. And whatever I do on the bottom, I must also do to the top. Okay, that's going to give us the cube root of 8x squared y all over 2x squared y cubed. If we want to show the whole process here, we can say that this is the cube root of 8x cubed. And look for opportunities to simplify. On the top, really I could split this apart as the cube root of 8 times the cube root of x squared y. On the bottom we have 2x squared y cubed times the cube root of 8x cubed is just 2x. Okay, almost done. These are pretty tedious. But sometimes you're asked to do this process that's called rationalizing the denominator, or making sure that you don't have any radicals down below. So our rule here is we want to get rid of radicals down below. No radicals in denominator. And you're probably saying, well, but I know that the tangent of 45 is 1 over root 2. Yeah, but if you rationalize it, it would be root 2 over 2. So depends what context you're working in, whether people are actually caring whether you rationalize the denominator or not. We can go further, but it gets painful. So what I'm saying here is that if we have an expression like this, we can't easily divide out. Our best plan here is to go to exponential notation and say this is x to the 3/5, y to the 2/5, all over 8 to the quarter, x to the 3/4, y to the 9 over 4, work through that way. You're going to have some fractional powers. In the end, if you want to put it back into radical form, that's fine. We're not going to spend a whole lot of time on that. Okay, so as I said, rationalize means to make the denominator a positive integer. So no radicals on the bottom. In this one over here, first one we have 3 over root 7. The question is, how can we get rid of a root 7 on the bottom? I can multiply by root 7, but if I do it to the bottom, I have to do it to the top. Because really what I'm multiplying by when I do that is 1. Root 7 over root 7 is just 1. That means my top is 3 root 7, and my bottom is root 7 times root 7, which you could call root 49, or better yet, just the number 7. Now, throw it in your calculator, see what the decimal approximation is. 3 divided by square root of 7, didn't need that, is 1.13. And if I have 3 root 7 divided by 7, guess what? It's the exact same thing. So 2 ways of writing the same expression. Generally, if you're going to rationalize, you're better off simplifying your expressions before rationalizing. So this is going to be root 15 over root 8 is just 2 root 2. Now you only have to multiply by a smaller radical, only by root 2 instead of by root 8, and there'll be no simplification at the end. So you get, or no reduction. Root 30 over 2 times root 2 times 2 is 2, or root 30 over 4. Again, you can always check that you've done it right to make sure that you get the same decimal approximation from this form as you did from the original. Okay, the last one is pretty important when it comes to some of the limits that you may end up doing next year. If we have root 5 over 2 minus root 2, you might say that I can get rid of the radicals by multiplying by root 2 over root 2. The radicals on the bottom. That'll give me root 10 over... Oh no! I just changed where the radical lives, so I still have a problem. The way out of this problem, when you have a binomial on the bottom, and part of it is a radical, or both parts are radicals, different radicals, is to recall this property, a plus b times a minus b. That's the way where you can get 2 perfect squares. It's kind of the perfect square factoring in reverse. And no middle term. Remember that these are called binomial conjugates. So in this case, we're going to use the conjugate of 2 minus root 2, which is 2 plus root 2. Let's see what happens. We're going to get 2 root 5 on the top plus root 10. That's okay. We're saying it's all right to have radicals on top. Now, for the bottom, we'll have 2 times 2, that makes 4, plus 2 root 2, minus 2 root 2, minus root 2 squared. Ooh, this is looking good. So that's going to be 2 root 5 plus root 10 all over 4 minus root 2 squared is just 2. Or 2 root 5 plus root 10 over 2. Now it turns out when you're doing some of the limits, sometimes you actually have to rationalize the numerator this way. So you're going to want to know about this whole binomial conjugate thing, so that if you saw a question that involved 2 different radicals separated by plus or minus, or an integer and a radical separated by a plus or minus, you'd know to multiply top and bottom by its conjugate. So there are some suggestions here for some practice work that's in the handouts, and the handouts is linked in the video description below.